Okay, so at this point we have looked at polynomials and graphing polynomials and all the rules for the graphs with behaviors around zeros and end behavior. Now we're going to look at rational functions, and essentially there's several rules similar to the rules we had for polynomials, and the easiest way to see how to graph these things is to just, we'll graph a few of them and run through all the properties and see how they work. So, suppose we have this. Y equals x squared minus 9 all over x cubed minus 25x. We want to graph that. The first thing we have to do is factor the top and bottom. So for this one, all of you can factor this. The top is the difference of squares. That's x plus 3 times x minus 3. The bottom, there's a common x that can factor out, and then I have x squared minus 25, which is x plus 5, x minus 5. Now I have it all factored out. Now I look for common factors on top and bottom that can cancel out. In this case, there's nothing that cancels out, so it's already in lowest terms. When we're kind of sketching our graphs, first thing we look for are holes in our graph. One thing to be aware of, when you're actually plugging this into a calculator, the graph on your calculator won't show the holes if there are any. So just be aware of that. If you're just going to use your calculator as a guide, it doesn't give you the correct graph. It doesn't give you the holes in the graph. But the way it works is, any factor that cancels out in the numerator and the denominator results in a hole in our graph. In this case, it's already in lowest terms. Nothing will cancel. So we have no holes. Next thing we care about, vertical asymptotes. Vertical asymptotes occur where the function is undefined. So in this case, vertical asymptotes occur where the function is undefined, which is where it's 0 in the denominator. So where is this 0 in the denominator? When x equals 0, when x equals negative 5, and when x equals positive 5. Next, find the zeros of your graph. The zeros of your graph occur where the function is 0 in the numerator. And in this case, that's at negative 3 and positive 3. After that, we can find the y-intercept. We don't necessarily need it, but a lot of times it will help us in sketching our graph. The problem in this case is, to find the y-intercept, set x equal to 0. But if I do that, this becomes 0 right here, which means it's 0 in the denominator, which means it's undefined, which means there is no y-intercept. And then the last thing we care about is horizontal or oblique asymptotes. Essentially, the horizontal or oblique asymptote is like the end behavior of a polynomial. It's what your function does when x gets really big or really small. And one thing that often confuses students, you do not have to look for the horizontal asymptotes and the oblique asymptotes. Your graph either has a horizontal or an oblique. So if you find out it has a horizontal asymptote, you don't need to look for the oblique one. There isn't one. It's either horizontal or oblique. And the way it works is, you look at the degrees of your numerator and your denominator. For this one, the degree of the numerator, the highest power of x is 2. The degree of the denominator, the highest power of x is 3. There are 3 possibilities. The degree in the numerator is less than the degree in the denominator, the degrees are equal, or the degree in the numerator is greater than the degree in the denominator. As far as it goes, if the degree in the numerator is less than the degree in the denominator, like we have here, we get a horizontal asymptote at y equals 0. Okay? If the degrees are the same, then you get a horizontal asymptote at what's called the quotient of the leading coefficients. Essentially, we're still going to graph this one, but if this was an x cubed and the degrees were the same, we would look at the leading coefficients, 1 and 1, and our horizontal asymptote would be at y equals 1 over 1, and that's it. So it's pretty straightforward. If the degree in the numerator is greater than the degree in the denominator, like if this was x to the 4th, and that was x cubed, well then the degree here would be greater than the degree here. Then to find your oblique asymptote, you have to do the long division out. Whatever answer you get from your long division is your oblique asymptote. I'm probably going to make another video after this one where I go through a couple of graphs of these things. So if you're not entirely sure about different horizontal and oblique asymptotes, I'll do a couple of examples on another one. This video is just going to be about all the properties. So here, since the degree is 2 over degree 3, degree in the numerator is less than degree in the denominator, it's horizontal at y equals 0. Now sketch the graph. So let's see, we have no holes. When you're graphing the holes, put them on at the end. Just kind of wait until you're done graphing everything, and then make a couple of holes. We don't have any, so we don't have to worry about it. We have vertical asymptotes at 0. That one you can't see, but it's on the axis. At -5. And at +5. We have zeros at 3 and -3, so we'll say that's -3. This is +3. We don't have a y-intercept, so we don't have to worry about that. And we have a horizontal asymptote at 0, which, much like this vertical one, is on the axis, so we can't see it, but we know it's there. And now we should be able to sketch the graph from there. Problem is, that's a little bit hard to figure out just by looking at it. So if this occurs, pick another value of x, plug it into your function. All you really care about is if it's positive or negative, because then you can use that as a guide to graph everything. So for this, we'll just use, since we can't use 0, suppose x equals 1. If x equals 1, you get 1 plus 3, which is 4, times 1 minus 3, which is -2, over 1 times 1 plus 5, which is 6, times 1 minus 5, which is -4. Let's see, the 4's cancel, the 2 cancels with the 6 and leaves a 3, the 2 negatives cancel, and we get 1/3. So we can sketch that at 1, we get 1/3, which we'll say is right here. Again, ultimately, all we really care about is if it's positive or negative. It's positive, so now we're good. Because much like with polynomials, we can connect the dots. So right here, we know the value are 1 and 3. They have to touch each other, so make it go down. Now, at 3, the behavior at this 0, the rule is the same as it was for polynomials. You look at the degree. At 3, that's x minus 3, degree 1. The rule says if the degree is odd, cut through the axis. So we cut through. Now I can either go up or down. If I go up, I give myself another 0, which from polynomials we know I can't. So I have to go down. And I approach my vertical asymptote. Anytime we're approaching an asymptote, a vertical one, you either approach -infinity or positive infinity. So this will just shoot down to -infinity. Now, the only other trick to this, the behavior around the asymptotes. Essentially, on this side of the asymptote, it either has to come from down here or come from up here. To figure out which one it is, we use the same rules we did for polynomials. For polynomials, we said if the degree is odd, you cut through the axis, or your sign switches. Here it switched from positive to negative. Same rule for the vertical asymptotes. You look at the degree. At x equals 5, that's x minus 5. The degree is odd, which means your sign switches. Here it switched from positive to negative. The rule is the same. Here, it's -infinity. So since it's odd degree, I have to switch. I have to have positive infinity. So I have to go up here. And then I just come down. The problem is, if I keep coming down, I'm going to eventually give myself a 0, and I don't have any more zeros. But that works because I have a horizontal asymptote at 0, which just means I come down and I approach it. I never actually hit 0. Now, on this side of the graph, well, let's see. We know there's a vertical asymptote at 0. Here, I can either go down or up. If I go down, I give myself another 0. I don't have any more zeros. So I have to go up. And I shoot up to infinity. Now the behavior around this 0 has to be the same rule as this. X is odd degree, x to the first, which means sign switches. Which means if this is positive, on this side it's negative. And then I come up. I have to hit my 0 at -3. And let's see, behavior at that 0, that's the degree for that 0. X plus 3 is odd degree, I cut through. So I cut through the axis, then I have to go up and approach infinity now. Behavior on this 0 is the same. That's -5, which is x plus 5, odd degree, so sign switches, which means it's positive on this side, so it's negative on this side. I come up. Again, there's no more zeros, but that works because I have a horizontal asymptote of 0. So I'll just approach it. And there we go. There's my graph. As far as the properties go, that's pretty much all you need. Factor it out. Any factors that cancel will give me holes. Then, once you've factored it and it's in lowest terms, zeros in the denominator are vertical asymptotes. Zeros in the numerator are the zeros of the function. For the y-intercept, just plug in x equal to 0 and solve it. And then look at the degrees to determine if the asymptote is horizontal or oblique. The last trick is, like we did here, if you plot all these points out and you still can't tell what your function's doing, pick a random point. All you really care about is if it's positive or negative. And once you pick that point, that should give you an idea of how to start connecting the dots and using the properties of the degrees here. That's the end of this video. And if you need more help, like I said, I'm going to post another video with a couple of examples of these.